Good morning, good afternoon, good evening, everybody, wherever you might be. It is my pleasure and honor to introduce my friend and colleague and collaborator, ANDRZEJ, who will tell us about the Riemannian geometry of a discretized circle and torus. It's all yours, take it away.
Okay, thank you very much, Piotr. Thank you, everybody, for being here. And it's a pleasure to give a talk in the North Atlantic, so joining Europe and the US and the Canada and maybe Mexico. I don't see whether Elmar is here. And the story is about the joint work with my two PhD students, Arkadiusz Bochniak and Paweł Zalewski. And that's a sort of, attempt to do something, with Riemannian geometry, generalizing Riemannian geometry to some simple, very, very simple spaces. Well, non-commutative, but in the sense of almost commutative, because the algebras of functions are commutative algebras. The differential graded algebras are behaving differently. And this is something, that was the part of a bigger project that's still, to be maybe extended in the future, and of the project to, relate this Riemannian geometry in this, so to say, algebraic sense. I will explain it to the Riemannian geometry that I have been, involved with Ludwig mostly, but also with Masoud in a sort of spectral sense. So, studying curvature through spectral, in just the spectral meaning, spectral sense. Now, of course, for the discretized circle and discretized things, this doesn't work because, from the spectral point of view, they're zero dimensional, but, there are other approaches and other ways. And then there's a good question of, passing between them. Anyway, so I need to now switch. Okay, so what is the motivation? The motivation is mostly gravity, because, well, we know that general relativity is nothing else but a theory of certain linear connections over spaces, over manifolds. And basically, when you do the Riemannian geometry, or rather pseudo-Riemannian geometry, so not for the Euclidean, but pseudo-Euclidean metric, pseudo-Riemannian metric, you do this theory of linear connections, compute curvature, scalar curvature. Then what you basically get is the Einstein theory of general relativity with some possible modifications. Now, these modifications of general relativity exist and they go in different directions. So you can make general relativity with some scalar fields, with some tensor fields. You can make general relativity with torsion. Well, you can make the theory of, say, two gravities, like this is also, the bimetric gravity. That's sort of, also done and studied and, in physical situation considered as some sort of alternative. But mostly, the good question is, of course, how to quantize gravity and how to make a passage from this classical picture of general relativity to something like a quantized version of gravity. This is still a mystery. I mean, in a way, many attempts, like starting from string theory, loop quantum gravity, just a general quantization of gravity, linearized gravity, or whatever. Still, I mean, there's no good answer. I mean, what it might be. Now, there is one thing that's been reiterated by many people, that to have the version of a quantum theory of gravity, you need something like a quantum theory of space. So space should be somehow quantized, and this is what quantum space-time is usually mentioned. And of course, there are several ways of doing it. So one of these aspects is based on, one of these approaches is just discretization. So you discretize the manifolds And you can do it, I mean, in many ways. I mean, usually when you discretize things for doing, for instance, lattice gauge theory, you discretize just things on a lattice. And you can try to discretize gravity on a lattice, but what's more popular is you discretize gravity like on triangulations of spaces. But there are other things. I mean, you can just, you know, go to some spin networks and spin firms, and I will not, you know, talk about it. But there's an idea that something, I mean, when you want to have effective approach to quantum gravity, or, you know, try to do something like quantizing gravity, you need to pass from this continuous or smooth description of spaces into, say, for instance, discretized spaces. Another thing is that, of course, you know, this quantum spacetime, there's this issue that you can just do Q-deformed or kappa-deformed or whatever. That's another line of, you know, understanding what quantum spacetime might be. So something like deforming the usual continuous spacetime. Okay, so this is the basic motivation. So if this is to some extent true, so if this discretization should work or works, then there's a good question. I mean, can it be approached not only as some sort of, you know, approximation, but can it be approached rigorously in this language of doing noncommutative geometry and doing Riemannian noncommutative geometry? So this is a possibility. This is a possible avenue. And well, one little remark that, you know, what is this Riemannian geometry of noncommutative spaces is still also to be understood. So one can treat all this as some sort of a toy example or some sort of a, you know, test ground for testing what this noncommutative Riemannian geometry is. I mean, as I mentioned, I mean, there are several things, and I've been involved in the approaches of something that could be called spectral approach to Riemannian geometry. So studying certain objects like scalar of curvature using spectral methods. But, you know, generally there are a couple of approaches. I mean, I list them under the four, so to say, names. First, one can say it's sort of naive approach. This is maybe, you know, sort of exaggeration, but basically that's been popular in some physics community, that you just write the like linear connection and the Riemann tensor in the just, you know, like you write it for the manifold or for Rn, just in the local coordinates. Then what you simply say, oh, these local coordinates do not commute, and you write, you know, what's this kind of curvature. There's another thing, which is the Moyal approach, which is more rigid. In the end, I mean, very, very similar, because I mean, most of the objects could be understood as some sort of generalization of the classical objects like the Ricci tensor, Riemann tensor, metric. The only difference is that they are not the usual functions. I mean, they usually, you know, something like functions or tensor value functions over the manifold, they replaced by, you know, the functions, but the products are not the usual products, but the Moyal products. Now there's the algebraic approach, and this talk would be mostly about the algebraic approach, so sort of fundamental approach based on the theory of differential calculi, which is very rigid and very well understood for the algebras, for all algebras in principle, starting with the universal calculus and then all the differential calculi, and especially for groups and especially for Hopf algebras. And then, I mean, starting with this object, you can try to build upon it the theory of linear connections, the theory of metric, and all the ingredients that you basically have in the classical Riemannian geometry. And then, of course, I mean, this is the last point, I mean, sort of historically, possibly, but, you know, the spectral approach, when you try to recover the objects in geometry, like, for instance, I mean, the scalar of curvature, using the study of spectral properties of certain operators like square of the Dirac operator, Laplace operator, or maybe something, even more generalized. And then, by studying, those asymptotics, basically the asymptotics of the spectra, you can recover some data. And this approach, is very, very good in studying classical objects like the usual Laplace operator, usual square of the Dirac operator over the manifold, spin manifolds, and is very, very difficult and tedious. And some people who are in the audience certainly can confirm it when computing, for instance, the scalar of curvature, even for simple objects like tori, two-dimensional tori, or even higher dimensional tori, with very, very mildly, so to say, perturbed metric from the flat metric. And even for the flat metric, sometimes that could be difficult. So this is sort of the review of the approaches. Just a listing of the approaches. The thing is that so far, the classical geometry, so the usual manifolds and Riemannian manifolds, is the only intersection of those things. Of course, naive approach is the same as the standard differential geometry approach and the standard algebraic approach and the spectral approach. So based on the heat trace, is giving the same answers. And this is computable and reasonable and consistent between all the methods. However, there are many examples of non-commutative geometries for which those approaches, could be applied, studied, and can give some answers. And this includes, well, not only classical geometries, for which, of course, this is done, but also, in some cases, Q deformations, so quantum spaces, like SUQ2, for instance. Well, certainly Moyal deformation, for which, there's been some examples of using this algebraic approach and studying the objects like the metric and the linear connections. Also fuzzy, some sort of finite spaces like fuzzy spaces, fuzzy tori, fuzzy spheres, twists, so deformations of usual manifolds by twists like non-commutative tori and twisted spheres, and also finite spaces. Okay. The only thing with this example, so for instance, if you take non-commutative tori, you can apply algebraic approach. You can apply spectral approach, studying, basically the same object. So if you try to perturb slightly the metric, or whatever the metric is, over the non-commutative torus, then what you do, you can study what could be the scalar of curvature. And the only thing is, the bottom result is that the answers do not match. So you get completely different answer from the spectral approach and completely different answer from the algebraic approach. So the question is, about the applicability of that. Now, if you want to study finite spaces, so spaces consisting of finite number of points, one can try, starting with the basic things, and the basic thing is, of course, 2 points, and I will mention that, and this is what many things have been concentrated on. Studying, just very, very simple examples. What we try to do, and what we somehow, we're trying to focus on, was first, in general, maybe trying to study what would be the non-commutative Riemannian geometry of finite groups. So finite groups, just, arbitrary finite groups, in particular, not only abelian finite groups, but as far as it went, the project, we started, first, on a very simple example of the cyclic group. So just, the simplest abelian group. with, however, not only Z2, but say endpoints, and trying to understand that was difficult enough and took, well, quite an amount of time. So if we try to go the algebraic way, we start with is a differential calculus. I'm saying the differential calculus because we'll be choosing one differential calculus for the considerations. I mean, of course, I mean, this is one of the weak points to some extent of the theory, because I mean, even if you have a finite group, even if you have a finite cyclic group, I mean, you have many differential calculi, and there's, you know, there's a sort of ambiguity in which one you shall choose. I mean, there are certainly some guidelines why some might be better than the other, but anyway, I mean, this is something that, you know, lives some freedom. So the differential calculus is just what I said is a differential graded algebra with a linear map satisfying the graded Leibniz rule. And the zero forms are just the elements of the algebra, and we have a wedge product. I mean, I'm using wedge, but it's not always anti-symmetric in generality. But anyway, I mean, here I don't use wedge, I just use the usual multiplication, I mean, to denote it. And what do we
sorry, could I have a question?
Sure.
Shouldn't it be there omega after -1 to omega?
Yes.
Oh yes. Oh yes. Oh yes. I do apologize. Of course, you know, this is somehow, you know, this omega got
Lost.
eaten somewhere by.
Okay, so it's 1-0 for us.
Excuse me?
It's 1-0 for us in spot.
Yes. This is, you know, I mean, I was too concentrated on writing probably this omega in -1 to the omega. So the omega. Yes, of course. So sorry for the omission. Anyway, so the next step, and this is the basic. So what is the linear connection? I mean, we take omega-1 as a left module. I mean, you can take it. This is a bimodule. So, you know, this would be the next step after this step. But at the moment, we're taking it as a left module, and we consider a linear map from omega-1 to omega-1 over a tensor over a omega-1 over a. So we take like the tensor product of one forms over the algebra and consider all linear maps from one left module to another left module that satisfy a version of the Leibniz rule. So this version of the Leibniz rule is that I mean, this is the usual version of the Leibniz rule for the connection of the left module. Okay, so far so good. This is a nice and standard definition. But I mean, as I said, you know, I said that the Riemannian geometry is the theory of Levi-Civita connections, but of course, Levi-Civita connections require more conditions. So what are those conditions? So first, it's what we need to think about is the bimodal compatibility, which we don't see in the classical picture of manifolds, because classically, when you multiply the forms from the left and from the right, it doesn't really matter. And the algebra is commutative, so the left and right multiplication is the same. So basically you can restrict yourself to the left module structure, it doesn't really matter. Then there's something which is the torsion freeness. And torsion and, well, the vanishing of torsion is something that, you know, has been sort of an issue when you consider connections, also Dirac operators and, well, even Laplace operators in non-commutative geometry, because for instance, I mean, when you consider the Dirac operator, even on a non-commutative torus or even on torus, I mean, there's a good question. I mean, this Dirac operator usually, I mean, it comes from lifting the Levi-Civita connection to the spinor bundle. And there's Levi-Civita connection in itself has this condition of being torsion-free. Now, by declaring, you know, Dirac operators as sort of given by certain conditions, I mean, we lose this torsion freeness, and actually we get a class of Dirac operators, Dirac type operators, which might include and includes operators that actually, I mean, classically have torsion. And this is, you know,
Andre, I mean, you forgot to say that the spectral action detects the right one because it.
Yeah. I was just about to say it.
Okay,
that
good.
there is a way, however, you know, to detect it in a classical case. And in a classical case, I mean, when you consider the action, the spectral action, and the spectral action, I mean, a part of the spectral action, actually, I mean, the one in 4 dimension given by the second term of the spectral action, which usually gives you the integration of the scalar of curvature. And if you consider it for the class of Dirac type operators for fixed metric, then, well, the minimum of this will come for the torsion free. So this is perfectly, you know, so there is a spectral way of fixing this by saying that you minimize certain term in the spectral action. However, I mean, there are some, you know, this might not necessarily work in the non-commutative case. And, you know, I mean, this is just a side remark that when you go and study it for examples of genuine non-commutative spaces, then it might not be that there is actually a minimum of that. So this is something, you know, that when you generalize it, it might be a little bit more difficult or might be replaced by something. So this is something classically it works. Nevertheless, there's still one more condition, which is compatibility with the metric. So if you go to the Levi-Civita connection, then this Levi-Civita connection has to be torsion free. Well, this bimodal compatibility you don't see classically, but compatibility with the metric. And there comes the question, what is the metric? And of course, I mean, there's the answer. I mean, from the spectra, in the spectral geometry, we have this answer that, you know, the metric is given by the Dirac operator and then the distances on the states between the states on the space of states. But I mean, in this algebraic approach, I mean, we need somehow like the algebraic formulation of what the metric is. And then, and this is, you know, all this and part of this, and this is, of course, has to be mentioned, and the reference given is the work of many people. And actually, you know, this sort of definition of the metric started in 90s something. Also, you know, many people like John Mador, Michel Dubois-Violette, myself, Dimakis, Miller-Huizen, and many other were involved in sort of versions of this defining the metric. But this definition actually, I mean, and there's been huge work by Edwin Becks and Shan Majid, and they just, you know, worked out, you know, many examples and the full theory of what this metric is, what the linear connections are. So this is following this approach. So a metric, I mean, is in this context pair. So one is like, say, in using the physical language, covariant and contravariant tensor. So one is like a tensor, so being the living in a tensor product of one forms, and the other is something like a dual object, which could be understood as a map from this tensor product of 1 for tensor square of one forms into the algebra itself. The only thing that, you know, of course, so if you take this product over the algebra, so you have the tensor product over the algebra of omega 1 with omega 1, and then this pairing, which is supposed to be a bimodule pairing, and this has to be compatible with each other in the sense that it's non-degenerate. So they like, in a way, I mean, you can say that one is the inverse of the other, I mean, just in quotation marks. And this is the precise formula, I mean, for saying that for any form, one form omega, this equality, this equation at the bottom should hold. But this condition, I mean, this condition, for instance, that this bracket is a bimodule map is very restrictive. And it's very restrictive in the sense that it limits the possible metrics that you can have. In many, many cases, it limits the metrics to, well, just very, very, one can say, you know, static case. So, for instance, I mean, if you take the, I mean, one example that, you know, probably everybody knows is noncommutative torus in noncommutative geometry. So if you take the noncommutative torus and you take the usual, well, differential calculus that's given by the two derivations over the algebra on noncommutative torus, and you take the one forms, and then you have the central one forms, and using, I mean, the basis of central one forms. And when you take this bracket, and since it has to be a bimodule map, so from this tensor product of the central one forms, which are the basis, it will need to go to the center of the algebra. But of course, the center of the algebra of the, if you have the noncommutative torus with the irrational deformation parameter, so theta is irrational, then of course the center of the algebra are just the complex numbers. So this is very highly restrictive, saying that in many, many cases, you would have only metrics that would give you something that you would probably consider, you know, a flat, or in physical terms, it might be, you know, very, very uninteresting, because it gives you no dynamics in a way. I mean, we're not talking about dynamics because everything is Riemannian, not pseudo-Riemannian, but anyway, I mean, it will give highly restrictive conditions on the metric. Okay, but let's take it as a definition. I mean, just having said these remarks, I mean, we want to proceed, I mean, and see it in a very example. Now, the torsion is actually easy in this case. I mean, the torsion is just a natural generalization of what the torsion in classical thing is. So you take one form D, and to the one form omega, and to the one form omega, you can apply either the exterior derivative D, or you can apply the linear connection nabla, and then you project it, I mean, by using the product in the differential algebra. So basically what you do, you project from the tensor product of one forms into the two forms. So this is quite easy. Now, a little bit.
Wait, Andre. So, but you restricted just to one forms, or you wanted to hold? Yeah, because you defined your nabla on omega 1A.
Yes.
Okay, I'll drop my question. You know what I wanted to ask? Whether you did a whole differential algebra.
No, I don't define the torsion. I don't extend it. So of course the linear connection can be extended to higher.
Yeah, exactly. Yeah.
So actually,
that's how you do curvature.
Well, so linear connection will be actually extended to forms of any degree tensor over the algebra one forms, and then the maps will go to the forms of the degree plus one tensor over the algebra one forms. So that's the, and this is how you basically then take the square of the linear connection to get the curvature and show the curvature is left module mapped, right?
Yeah,
but,
exactly.
Yeah, but torsion is just something that, you know, acts on one forms, and then, well, you just, you know, the torsion free condition is just, you require that this is identically zero. Now, the bimodule compatibility is a little bit more involved. And, you know, over the years, I mean, this is just sort of historical remark. Over the years, I mean, it's been sort of unclear what to do, because, I mean, of course, there are many possibilities. I mean, one can say that one can work only just, you know, with the left modules and just forget about the right module structure, just ignore it. Or one can impose some sort of compatibility with the bimodal structure. And I mean, again, over the years, you know, this thing with compatibility, you know, something grew stronger because there were many motivating examples. So we follow this path, and this is again due to Edwin and Sean, that what we assume is that there exists a bimodule map between the tensor square of one forms and itself. So you take omega 1 over a tensor over a omega 1, and you assume that there is a, and the name is that's used is some of generalized braiding. I mean, generally, I mean, it will be like a flip. But of course, you know, classically it's sort of trivial, but I mean, non-commutatively, it's not, and we'll see it actually. And then what you say that, of course, you know, the first line of the condition for the linear connection is just the definition of what a linear connection is. So acting on A, multiplying the omega from the Levi just gives dA, but you want it to be to some extent similar on when you multiply the one form from the right by an element of the algebra. But of course, you know, so the first part is natural because you still land in omega 1 tensor omega 1, but then you need to flip it somehow. So this omega tensor dA, I mean, to have the roles inverse. And so for this, you just assume that there is a sigma, which is a bimodule map. And this is the basis of assumptions. Now, for the sigma is also actually quite helpful and quite, you know, fundamental for understanding the compatibility with the metric. Why? Because you remember, I mean, if you remember, you know, the metric was also an element of this tensor product over A. So, I mean, then you can also multiply the metric, you know, when you multiply this metric from the left, from the right, you know, you need to have compatibility with the action of the linear connection. So a linear connection, so this pair, nabla and sigma, is defined to be compatible with the metric again, and the metric is taken as this metric tensor living in the differential forms, tensor differential forms. If you're applying this nabla to the left leg, so to say, of this G, and applying to the right leg, but then you need to flip this. So this is where this sigma comes in, and you add those things, gives you 0. So, and I mean, you can see, I mean, you can convince yourself that if you write the classical metric in this form, so for a manifold, and you apply the linear connection, then what you usually get is the compatibility of the metric with the condition, with the linear connection. So this is, you know, so far established notion of what a linear connection compatible with the metric and torsion-free can be. Okay, there's a little bit more because, well, so far I haven't mentioned, but usually when you have an algebra, like the algebra of complex valued functions of even a discrete set, like we'll be taking, then you have natural stars, so a complex conjugation of a function. And well, if you have a star in the algebra, you can extend it. You can look for the differential calculi for which this star extends. So star compatible differential calculi. And then you can ask whether the metric and also the linear connections can or are compatible with star. So for example, I mean, if you take the metric, so the usual notion is that the metric will be star compatible if G star is just G. And here, know that if G, I mean, this is like using sometimes the Swidler notation in this tensor product. So G could be written as G1 tensor over A G2, and there's a summation involved. So G and this one in brackets are just one forms, G2 in the brackets are also one forms, and then you make the flip. So you, of course, I mean, just to have the compatibility with the tensor product with the multiplication by the algebra elements. And for this bracket, I mean, this is also in this way.
Yeah, about the bracket, I should have asked this question much earlier. So how is it given? Is it just some additional part of the structure that can be picked up differently, or is it somehow given canonically? I understand it's some kind of nice pairing on omega 1A with itself. Do you have it?
It is fixed. It is fixed. So I mean, the two are related. You will see the, so the best way would be to see it in an example. So once you have the first, you have the second.
Excuse me, and this notion of compatibility with a metric doesn't use this pairing.
Well, you can express it using the pairing as well. No, but I mean,
of G, yes.
Sorry?
Instead of using G.
Instead of using G, you can use it. You can use the brackets. Yeah.
Okay.
Okay. So now, generally, if you go to abstract non-commutative spaces, so if you go to say in algebra, differential calculus, and you ask the question whether such metrics do exist, I have no idea whether this is guaranteed in generality.
Do it now.
In many examples, I mean, this does exist. However, I mean, as I mentioned, you know, there are huge restrictions on such metrics. And for instance, you know, for the non-commutative torus, I mean, the only the constant flat metrics in this sense are admissible. So this is something like this, there's a price to pay, and sometimes there might not be even, you know, well-defined metrics. Now,
excuse me, so just a quick question. So you mean such metrics, you mean all these conditions, yes? Compatibility with...
No, just the metrics. I'm saying, so the first statement is just about the metrics in this sense, not even about the linear connections.
Uh-huh. Okay.
Now, the existence, so, but of course, you know, for some quite, you know, well understood situations, like for instance, I mean, non-commutative tori, like the discrete spaces, like say even Moyal deformation, the quantum spaces, quantum SU2, some differential calculi for quantum SU2. It's known that such metrics do exist. And then there's a question, I mean, so if these metrics do exist, so there's a question whether for these metrics there exist linear connections that are torsion-free and metric compatible. So in a way, just you can say generalized Levi-Civita connections. And in some some special cases, so if you study, you know, certain differential calculi, if you study certain examples, this can be shown to be true. So the existence can be shown to be assured. And you will see that the existence, I mean, for instance, for these finite spaces, finite discrete sets understood as Zn, or, you know, sort of fuzzy circles, that the existence is quite easy to show. Well, maybe not easy, but the existence is sort of assured. The uniqueness is much more involved in, and again, this happens in very special cases, and this is the reference to some recent works by Goswami, Landi, and co-workers. Okay, now finite groups. So this fuzzy circle. Why finite groups? So first, say the toy examples and some physical background meaning that, I mean, we all know that the Z2 is sort of this finite toy model, the toy model of this finite discrete space in this generalization in the non-commutative description of the standard model. So if you take, you know, this sort of toy model with only 2 points, this is you know, this discrete space. You can extend it, you know, to 3 points, many points. You can extend it to different algebras. But anyway, I mean, the sort of story is similar. Then, of course, I mean, it's very nice because it has group structure. So you can use all the tools. I mean, this is like, you know, using big tools for very simple object. But anyway, you can use the tools of the bicovariant differential calculi. So the natural differential calculi for the functions over a group. And basically, I mean, it's something that when you look at Zn as some sort of this fuzzy circle, then you can look, okay, one can think about continuous limits. So you can see it as some approximation of a circle. Of course, circle unknown maybe is, you know, is one-dimensional, it's very naive, it's very sort of trivial. But in a sense, I mean, one can then try to take product of circles. So thinking about, you know, fuzzy torus, but not in a fuzzy torus that's done by matrices, but then done by products of fuzzy circles. So this is something, you know, slightly a different angle. And there was a question, I mean, how far one can go? Do the connections exist? Well, this is, you know, something like doable, you know, to show that they exist. But, you know, if you go to the limit, what is the answer of the connection? What it actually depicts? And if you compute the curvature, what it gives? So I would try to give you the answer in the end. What is the curvature for a Levi-Civita connection of a fuzzy circle, which is funny thing that it exists. Anyway, so then you can extend to fuzzy tori. I will mention it in the very end, but fuzzy tori, in this sense, as products of fuzzy circles, are more complicated. So what is the basics we start with? So what is the differential calculus we start with? So what do? We consider the minimal differential calculus. The minimal in the following sense. So we take the cyclic group Zn. The thing is, I take here n bigger than 2, but actually what we will do, we'll take n big. So we take n bigger than 4 for certain reasons. And this will be, at the moment, you know, for the differential calculus, this is bigger than 2. With the generator P, so P is just 1. If you take the Zn group identified with 0, 1 to n minus 1, then P is just 1. And by P tilde, I don't know its inverse. So it is minus 1 or modulo n, so just n minus 1. And why taking n different than 2? Of course, because then P is different from P tilde. That's you know, Z2 is a special case. I will make a short comment about Z2. Now, what I take as a differential calculus is the minimal bicovariant star compatible connected differential calculus, and this calculus is generated by, I mean, the bimodule, the left module of one forms is free, generated by 2 one forms, which I denote by theta p and theta p tilde. And the bimodule rules are just that if you push f from the left-hand side to the right-hand side through theta p, rp is the right shift on the space, so just shift by 1 to the right. So if you push it through the theta p tilde, it's then shifts, you know, to the right by the inverse of p. And then there is a star, so the calculus is star compatible, and the star of one of the form theta p is minus theta p tilde. The calculus is inner, so the differential of any function could be written as a commutator with the sum of this one forms, and then you can extend it. I mean, this is using the Voronowicz bicovariant differential calculus structure for this very simple object. You can extend to higher differential forms, and this is one interesting thing. This calculus has dimension 2, so that there exists a 2 form, which is non-trivial, and this is just the product of Tp and Tp tilde, and this is antisymmetric. So Tp wedge Tp tilde is minus Tp tilde theta p, and of course the wedge. So the wedge is antisymmetric. I mean, as in this bicovariant calculate for the abelian groups.
Andrzej, what do you mean by connected?
Connected, I mean that basically the one forms are generated by D, and only then the kernel of D are the constant functions. So these are the assumptions about the differential calculus. Okay, now this is again using the results. So far, you know, the results are the general results. I know which we basically recovered, I mean, are the results, you know, that are used by Sean and Edwin, that if you have the inner calculus, then the bimodal connection is in fact determined by two maps. One map is a sigma, which is a bimodule map between omega 1 tensor omega 1. I didn't write over A, but here all the tensor products are over A. And another map, which is a bimodule map from omega 1 to omega 1 tensor omega 1. And the first result is that if you take n bigger than 3, actually, I mean, this is our assumption was n is bigger than 2, and here we take n bigger than 3, then actually only this bimodule map sigma determines the connection, because then there's no bimodule map between omega 1 and the tensor product of omega 1 and omega 1. So actually here, this alpha for n bigger than 3 is identically 0. So the bimodal connection and sigma are mutually determined. And this sigma is the sigma that appears in this definition of the compatibility connection of the for the bimodal structure. So if you have this pair nabla sigma, so here actually you have only sigma. So,
and when you say a minimal calculus, do you mean that there is more than one, but you have like a bunch of different minimal bicovariant calculi? Or is it?
Well, depends what you mean by minimal. I mean, minimal, what I mean is that so to say, the number of one forms that generate the bimodal of one forms, they generate the bimodal of one forms as a left module is minimal. So the minimal is one form, but this is not star compatible unless n is 2. But if you have two one forms that generate as a left module, then this is the minimal. But of course you can go farther. So this is, yeah, there exists a minimal, but this is the minimal, right? So a minimal in the sense that the minimal is, you know, star compatible requires a little bit. The minimal, there's only one. Well, what you can do, yeah, you can write the difference, but that's not that important. Okay, now you can make this calculus. So since there's a wedge product in this calculus, you can make the connection torsion free, and the condition that the connection is torsion free is the condition again on the map sigma. And I will just write it. I mean, this is nothing, you know, very deep. You just do it by checking the conditions, and these conditions, you know, the important thing is that they could be met, they could be satisfied. But then, you know, you look, what are the possible maps sigma? So what is the freedom of linear connections? And then, you know, this is the, you know, the first result, you know, that shows you that there's a plenty of linear connections. I mean, so far not, I mean, we're not saying, you know, torsion free. So if you have torsion free, so the proposition is for torsion free. If you don't require torsion free, then there's a bit more. So there's a little bit more of coefficients. But this looks like, you know, something like coefficients for a torsion-free connection. So actually, any torsion-free linear connection over this calculus is given uniquely determined by 4 functions. So what you do, you just reduce the problem from finding some maps to finding some functions. So if you have 4 functions, and I denote these functions by A and B with indices P and P tilde, then this gives you this map sigma and in consequence a linear connection. Here, this is, you know, again, you know, direct computation. And here we need to assume that n is bigger than 4. Why bigger than 4? Because if you have n equals 4, then p square is the same, is actually p tilde square. So then it's, then you have more conditions, and sorry, more freedom. So you have extra freedom.
So when you write not equal, you mean actually bigger?
Yes, because I mean, we assumed bigger than 2, then different from 3, and this is additional condition bigger, different than 4. So actually later we'll write bigger than 4. So then there's a condition, I mean, which I will only flash because I mean, I will not concentrate on them in a moment, but they are much more complicated. These are the conditions that what it means for this linear connection to be star compatible. So there was a notion of star compatibility of the connection. I will not, go into that. But then we need to introduce the metric. And here is something, that, tells you what this metric is. So the metric is first, I mean, you can define it as a tensor. So this is the first tensor. It's uniquely defined by 2 functions, GP and GP tilde. So functions on this first circle, so on these endpoints. And well, equivalently, you can say you can find this product. So you can see that one is actually fixing the other. So if you have the metric G, then it gives you this product, which is defined on these forms. So actually, this is the only non-trivial is between theta p and theta p tilde. And this is defined by those functions. And you notice that this function, I mean, this is like exactly the inverse. So in this definition of G, I mean, we took the G in the definition of this tensor, and then the inverse appears in the definition of this bracket. And you can require a little bit more. So you can require this metric to be star compatible, for instance, and there will be also, discussed. I mean, basically, if you require star compatible, then this function needs to be real. But if you require that the metric is compatible with the higher order differential calculus, so it simply means, I mean, remember that recall that this metric is an element in the one forms tensor one forms over the algebra. So we can project it onto the 2 forms, and you require that this projection of the metric is 0. This is the classical case when you say that the metric is symmetric. Then you have only one function. So this is the function that's then the GP, then the 2 functions needs to be equal to each other. So this is something which, I mean, is not obvious. I mean, there are a lot of conditions that are not necessarily obvious that you can impose. Okay. And there's another thing. You can ask a question. This will come out later on. So this is why I mentioned what happens. So if you have this metric, so if you have this G, and you can you try to make something like a scalar product between the forms. So you take 2 one forms, you make this star of, you conjugate first, and you compute the brackets, and this is in the element of the algebra, and then you ask, I mean, this is only, finite dimensional, because basically, I mean, you have the algebra is the algebra of functions. So this is like, I mean, this algebra of functions is actually, something like diagonal matrices or something like that. So this is quite easy. So using, using this sophisticated C-star module, language is maybe an exaggeration, but anyway, you just require where this will satisfy, the condition that this is actually Hilbert C-star module. And then there's if all these are real and negative, actually negative because of the switch in the sign for the star conjugation of one form, it happens. So there are some conditions, natural conditions that require reality and, sort of, well, actually, you know, with the minus positivity, if you add the minus sign, positivity of these functions, to have some sort of natural structure that allows you to have something like the scalar product of one forms. Okay, and then you can go for the left and right invariant metrics, because you have the group structure. Then you can impose such things like metrics that are left or right invariant, and then so on and so forth. And well, maybe we'll go into that later. So there's a lot of structure because of this group structure that you can have. Okay, now a sort of a warm-up case. I mean, this is, we've been talking about this minimal calculus for n bigger than 4, but of course, you know, there's a special case and very well-studied case for Z2, so just 2 points. So what is the space of linear connections and curvature and whatever on Z2? And of course, you know, on Z2, you have only one generating one form, theta p, because p is equal to p tilde, and then, you know, these conditions are slightly different. But, you know, cutting it short, you know, the linear connection is given by one function, and you can call this function S. The metric is given by one function, and this metric could be given G. So these are functions. So function on 2 points is just 2 complex numbers, right? So then if you just denote G0 to be G of 0, and G1, G of 1 for Z2, and the same for S, then you can write what is the metric compatibility condition. You can solve it, because I mean, these conditions are just, you know, very easy, you know, solvable. And then you can see that even if the metric is constant, and the metric, I mean, actually there's a condition that the metric needs to be, G1 needs to be plus or minus G0. So if you have the same sign, so if the metric has to have constant sign, so say negative or positive, then it needs to be constant. And then if not, the other needs to be the minus of, one has to be the minus of the other. So anyway, if it's constant, nevertheless, you're going to have metric compatible connections that are given by, you know, given by one number. So you have a lot of freedom, actually. And the question will be, well, is this freedom bigger or is the freedom smaller if you go to more points? So this is, you know, and this is, you know, well studied, and this is this is one of the examples in the book by Edwin and Shaw. Now, for the Zn, you have the metric compatibility condition, which results in actually 6 equations. So these equations are written for G. So G could be either P or P tilde. So P or minus P in this notation for Zn. And they are, so these are equations. So you remember, if you recall, I mean, this linear connection was given by a set of functions A and B for P and P tilde, and the metric was given by G. And these are the highly involved nonlinear recurrence relations, so sort of recurrence relations for the compatibility between the metric and the linear connection. And okay, the aim was to solve it, and well, solve it first in full generality, because I mean, if you go, for instance, you know, to the case of classical geometry, then if you have torsion-free metric compatible linear connection, you can solve it. So you can find the linear connection using the metric. And now the question was, if we solve this, can we actually recover from the metric the linear connection? So is there something like the uniqueness, and is the linear connection given by the metric? And the answer is yes, under certain conditions. So, and of course, you know, the so to say ultimate task, and we'll come to that, was to compute the curvature. Okay, so computing the curvature will be in the end, but first, you know, using certain tricks, so some rescaling. I mean, these are functions, so functions you just can rescale by subtracting one. So the small ag and the small bg are just a and b, shifted by one. You introduce a certain function which is the ratio of the so this gg and g inverse, so something like gp and gp tilde are like two component functions of the metric, and there could be something like the interpretation of them. I mean, in terms of distances, I mean, this is some sort of vague interpretation that you can have, that if you go from one point to the right, then this value of this function g, say gp, going to the right, would be like the distance between a point and point to the right, and the value of the function gp tilde would be the value would be like the distance of going from this point to the left. And of course, this is counterintuitive, but this is like telling you the distances going to the right are the different a priori distances going to the left. In this calculus, in this formulation of the metric, this could be interpreted like that. Anyway, and then this xg is like the ratio of those distances, for the one point, because I mean, if you go from one point to the right, this is not the same sort of part that you're going to the left. So this right and left distance between these 2 points, I mean, one function needs to be shifted, and this is like that. Okay, and if you use this xg, then you can actually obtain a very nice recurrence relations for this ratio xg. And this ratio xg, I mean, satisfies something that's, here at the bottom, which is just, a recurrence relation on a circle, that if you take this xg and the inverse of a shifted xg, it's constant. So this constant is something, that fixes, to some extent, possible, say, linear connections, possible geometries. And in a way, I mean, it could be arbitrary. We can see, however, I mean, it could be arbitrary, and we'll see, what it becomes and, what it is. There's a very special case when it is one, or actually, I mean, it's, I think it will be two because xg is one in this case, and then this is actually a very special case that's been discussed earlier in papers by Erwin and Sharp. Okay, now if you write explicitly this recurrence relation, I mean, just rewriting it, so using xp as a function of n, where n goes from 0 to n minus 1. So actually, I mean, you can just write as a function over points, and f0 is just equal to fn. Then you can explicitly solve it, and I just write you the solution, and this is the solution here, the second formula on the slide. But then there's actually, the theorem that sort of summarizes the construction of linear connections. So if you take this minimal calculus on Zn, n bigger than 4, well, this is h, p tilde simply means that there are two forms, and you consider torsion-free connections which are compatible with the metric G that was given by these two maps, GP and GP tilde, then the connections are determined by this map sigma, and this map sigma was given by AG and BG, and those functions AG, this functions AG is actually determined by the metric and actually the functions BG, so the other functions. So we reduce the freedom, and there are several possibilities which depend on the solution xg. So there are non-trivial solutions, and there are actually many possibilities for the linear connections that are torsion-free and compatible with the metric.
Andrzej, can you remind me, please, what is the bimodule map sigma in this concrete case? What's the formula?
Yes. So the bimodule map sigma was, so that was this.
Okay.
So these functions AP, AP tilde, BP, and BP tilde were just arbitrary functions that these are the only possible map sigma with these functions AP, AP tilde, BP, BP tilde. And those functions, I mean, if you, and then the linear connection is also determined by sigma, so it's determined by these functions. And then the question was whether we can fix these functions for the using metric, was using the torsion-free and metric compatibility. So
and what was the principle allowing you to fix sigma so explicitly?
Oh, this is the principle of being having this pair of linear connections which are compatible with the bimodule structure. So there's this compatibility of the bimodule structure with the connection. So this fixes the linear connection. But here sigma is fixed just by the bimodule properties of the one forms.
Yeah, because it must be a bimodule map, and you are saying
it must be a bimodule map, exactly.
Then this is simply the only bimodule map? No.
Yeah, this is the only bimodule map between the
now
omega 1 tensor omega 1 into itself. Yeah.
Thank you so much.
Okay, so coming back to this theorem, so it simply means that there's the solutions are given by the AG is fixed once you have G and B, but well, the solution for B is depending on X, and X can have many solutions. So the solutions are given. I mean, then this is, the parameterization of the solutions. Parameterization of the solution just as explicit functions is given by the parameters L, which go from 1 to n-1, and some arbitrary constants satisfying certain conditions. And this L is actually related to this constant C that we had before. And this constant C was from this recurrence relation that X was satisfying. And there are solutions for B, and I just, flash the results because this is, something that there are also many cases that this B, small b, is just given by X but not uniquely. So there are certain possibilities, and these certain solutions are not identical to each other. So there are several cases, and I will not even, given, that the time is running and I want to show you the sort of bottom line as well, I will not go into details. I mean, this is just, tedious and hard work. Fortunately, in a team with two excellent students who I suppose are in the audience, is a pleasure to do. Anyway, so this was case one. There's also a case two which is a very special case, and this is where this function xg, so this ratio of the left and right distance, so to say, between the points is constant. So of course, if you say that this is one, it simply means that the distance going to the right and distance going to the left is the same. But a priori, this is like, our sort of imagination. So maybe, going to the right and to the left is not the same, but they are related. Maybe there's a constant ratio, and this constant ratio is just saying that for this, there are some other special solutions. Anyway, unique solutions is where xp is -1. This is not actually that crucial. There is something when you require that the metric is star compatible. So G is G star. Then the constant solutions are restricted to real constants. Non-constant are restricted by saying that phi, that a priori was complex, is real parameter. But there's one thing. If you take the solutions, if you require that the solutions come from a real metric G that actually gives this Hilbert-System module structure. So these functions G are positive, or so negative, so minus G, minus GP, and minus GP tilde are actually positive, then the only solutions are for xg are the constant solutions. So, you know, this sort of requirement that these distances are positive. So this is not, you know, something like abstract tensor, but tensor giving some sort of information, maybe geometrical information on distances, on how you go to the left, how you go to the right, gives you some more information and restricts the possibilities. Still, this is not unique because this xg is constant. You can go farther and assume that the metric is compatible with the differential calculus. So this wedge of G is 0, and then GP is given to GP tilde. So it simply means this constant solutions is given by xg being 1, and then you can just recover the metric from xn in priori. But if you add this Hilbert-System module structure, then you have just uniqueness. So if you have this metric that gives you this Hilbert-System module structure on omega 1, there's a unique torsion-free given by the metric G, and if you require that this metric G has this wedge G being 0, then there's a unique torsion-free metric compatible, star-compatible linear connection. This is nice.
Hello, good morning. I'm okay, thanks. How are you?
Okay, there's some sort of interference, but anyway, I go to the next step, and this will be the last step. Okay, so we have these connections. So if you have connections, then this is the natural thing. You compute the curvature. So here the curvature is exactly, I mean, what Piotr was mentioning and asking actually in the first instance, in the first part of the talk. You just compute the square of the linear connection, and then the square of the linear connection is a map from omega 1, you understand, is an omega 1 to omega 2 tensor omega 1. And of course, this extends, you know, as you know, the square extends to the maps from higher to higher plus 2. This is the formula. And you just do it in that case. In that case, you have only one two form, which is just this theta p wedge, theta p inverse, so theta p tilde. And well, so you can express this. So actually, this curvature is determined by one function. I just write this function as rho g. And this function, I mean, could be, one form. This is rho g is actually a one form because, I mean, the curvature, I mean, this is, there's one two form, but on the right hand side, you have one forms. So rho g is a one form. So this is a unique one form. And this unique one form is determined by two functions. So you have this one form, which is just you express using this theta, say g, theta p inverse. And these are explicitly written, those two functions. So you put it for p, and this gives you the coefficient with theta p and theta p inverse. And well, you proceed further to compute something, well, tangible, like a Ricci tensor. And this is again, you know, using this metric and using this bracket, you can define the Ricci tensor as some sort of contraction of the curvature. And this is, again, you know, in this concept of bimodule connections and bimodule metric compatible linear connection, this is what's been used in this Riemannian geometry program by Edwin and Sean.
So I is just a bimodule splitting, Andrzej. I from omega 2 to omega 1 tensor omega 1 is just a bimodule splitting of this surjection multiplication map.
Yes, exactly. So sorry, I forgot to mention it. Yes, well, and this is also where actually an additional freedom comes to the entire construction, because this is, you know, this is not really determined, you know, by whatever principle. So you can have some freedom here, and we'll see that freedom. So this is additional, ingredient, that need to be added. But once you add it, you compute the Ricci tensor, well, what you call a Ricci tensor, so this Ricci object, which will be just, an object in omega-1 tensor omega-1, and you just contract it further, compute the scalar of curvature. And computing the scalar of curvature, so computing a function is just then fun. And well, what do we use here for our differential calculus? We use the map iota just to be, well, theta p tilde to have one parameter, because you can have one parameter because the wedge product is antisymmetric, so you can just make it the tensor product of theta p and theta p tilde plus anything that's in the symmetric part, and you can use this freedom, and then you can compute explicitly what is Ricci, and Ricci is just like that, doesn't really matter, and then you can compute what is the scalar of curvature. And here we computed for the special case xp being constants, gamma bigger than 0, metric g, which is less than 0, and still there are certain possible cases and solutions. So in these cases and solutions for the linear connections are just given here. So they differ by this coefficients in this linear connection that were in this map sigma b. In one cases it's just 1 and 1, 1 and 1 minus 1 over gamma, and there's minus gamma and 1. So there are actually 3 possible cases of solutions for the linear connection. And for each of them, you can compute this Ricci, and you can compute the scalar of curvature as a function. And this is computed using, well, certain functions z s that use the metric. And here the metric is this, this is the G metric. I mean, is only one coefficient because x, which is the ratio of these two metrics, is constant. So you can use only one. So the left and right, gamma is this ratio of this left and right. And you can explicitly compute it. And, well, if you take gamma being 1, for instance, so the left and right symmetric metric, and the standard choice of the lift, so the standard choice of the lift is beta being -1/2, so you just take the antisymmetric, so you antisymmetrize in the tensor product. You can do it here. In this special case, you can do it. And then you get a very nice explicit formula for the scalar of curvature as a function depending on this metric, which, funnily enough, differs by the sign for the cases. So the cases, differ just, by the sign. The result is just the same, but it has different sign. Okay. There's a generalization if you take some arbitrary functions BP, and so not really restricting, to constant case. But that's another thing. Forget about the last formula. Anyway.
And just a silly question.
Yeah.
This lowercase n, this runs your group Zn. Am I right?
Exactly. So this is a function. So R is a function. Small n is 0 to n, and n minus 1. And this is an explicit formula what this scalar of curvature is as a function for each n. And well, you can ask two questions. So first you can plot it. So this is where you can actually, compute it. So you can put it on a computer, you can take a metric, you can plot it, and you can also ask for the continuous limit. Why? Because, if you imagine you take a circle, you put a circle, you put many points into the circle, and you just look, here you have, some finite, differences, sums. So you can try to look what would be the continuous limit. And the continuous limit could be expressed as a, gentle formula using function g of t and its derivatives. So if g of t is a function that, say, well, on a circle, on an interval, will give you this metric. So this treat this as a sort of continuous limit for this g of n, and use the, well, d by dt will be like taking the differences, and then you define and take it once again d by dt. So continuous limit of this expression is like that. What it actually, means, what is the meaning of that, for the circle, for the line, for an interval, is something, that probably needs to be tested and studied. But anyway,
I think I might have an answer to this question. Namely, it was in the previous talk that I was mentioning that, in the work of Michel Herman on the diffeomorphisms of the circle, there was an expression which was involved and which we also used with Henri and Moscovici in our work on off algebra. And this expression was the differential of the logarithm of the Jacobian. Now, the expression you have here is very, very close, because after all, what you do, you take the differential of a logarithmic derivative.
Exactly. And so there might be,
So, I mean, I think this could be quite interesting, actually. I mean, so far, I mean, I was not convinced by your talk, but I mean, this is very interesting. Yes.
You see, this is, I mean, okay, this is, I understand, this is the approach, that's purely algebraic, but
Yeah, sure. No, I mean, okay, I if you want, okay, I'm not surprised by the fact that one can imitate all what was done in ordinary Riemannian geometry by working purely algebraically. Then the problem is to take the right bifurcations at the right time, because there
exactly.
Yes.
Exactly.
But this expression is interesting. There is no doubt. I mean, except that, of course, G of t is not a diffeomorphism. It's something which plays a role of metric. So, but the expression is interesting. There is no doubt. I mean, it's related to the Schwarzian derivative. You have to look at.
Yes. So this is related to the Schwarzian derivative, certainly. So you see, going all this way, and exactly, I mean, you need to take some certain steps and certain assumptions and make some right choices. But it gets you to something that might have some deeper meaning, and this is what it was all about, to somehow recover this deeper meaning. Okay, but then you can do just since people are doing simulations and people are just putting things on a computer, so you can just compute what it is for certain things. So for instance, take an ellipse and partition the ellipse. So the idea is to partially same angles, and then the distances come different. And I mean, this is the plot for 10. But if you do it for, say, 100, and you plot what the metric is, and you can compute it and plot the scalar curvature. So you can look for the, exactly in this meaning, you can look for these objects. I don't think, they have, very deep physical meaning, but there might be some geometrical meaning to that. And then, I mean, on the other hand, you can reverse the problem, and you can just, for instance, look, okay, so you have one of the things, that you look at is what would be the metric, so what would be the distances, and this is a standard thing in, in geometry, look for when the scalar curvature is constant, positive, or constant, negative. And then you have very funny behavior for the metrics. So you can, of course, take some assumptions. What is the metric at certain interval? But then the rest you can iterate and compute. And this is like, it's more for a line. But these things could be done on not only on a circle, but could be done for Z. So it could be done for a sort of a one-dimensional lattice. And then you can ask, you can compute what's the positive scalar curvature, what's the negative scalar curvature. And this is, sort of funny behavior, I mean, completely different. One is oscillating, the one is, tending to zero. So it's something, that, I mean, these questions, this is a very naive toy model, one-dimensional. But then, you can try to go further, for instance, to the torus. So briefly, in the last 1 minute or 5 minutes, I will say, what could be done for the torus.
6 minutes.
6 minutes. So what could be done for the torus? So just why torus? Because this is something like, you know, trying to do the, I mean, like trying to do something relevant for comparing it with the classical torus, fuzzy tori in a different way, different approximation, and also the non-commutative torus, and trying to see whether, you know, those methods somehow would converge. And then, you know, when you have these methods like algebraic methods, of course, the natural question would be to see whether some spectral methods could be used. And this maybe I will talk in the conclusions whether what would be the idea for the spectral methods. But anyway, if you look at the products of fuzzy circles, so products of ZNs, then well, I mean, you can repeat the sort of project, I mean, and try to compute the coefficients. The only thing is that the number of these coefficients grows significantly, and this is much, much more. I mean, and I'm talking here about, you know, the linear connections and the metrics, which are not necessarily the product ones. So not something that we have a connection on one circle, on the other circle, and we take the products of them. Just looking, you know, for the connections, linear connections that would be torsion-free, compatible with the metric that's, you know, allowed in full generality. And then, actually, you know, this is something like we failed to provide a similar analysis of the solutions. I mean, we only have the actually non-uniqueness solution for even for the case of the constant metric. So if you assume that the metric is constant, so just, you know, the shift on each fuzzy circle, I mean, doesn't change anything. I mean, this is just the functions that give it are constant functions. Even then, I mean, for this two-dimensional case, I mean, there are some non-trivial, non-unique solutions for the linear connection. So at the moment, I mean, we are still far from even fixing the conditions that would allow the uniqueness in this case. The idea is that the conditions for the positivity, for the giving the correct something like the Hilbert space, Hilbert module structure for the bimodal of one forms would be sufficient, but so far we have no proof of that, even for the product of two circles, not even mentioning many circles. So this is, you know, something that shows that this algebraic picture is, I mean, it has some deficiencies. Okay. Now there's the reference. This is based on the joint paper, Riemannian geometry of a discretized circle and torus. I focus on a circle because this is more, I mean, for torus, we have this basically non-result, so the result of non-uniqueness for a special case. And basically only in the intuition that it might go better if you require much, much more, but this is tough. But what is the method? So first, well, this sort of algebraic generalization of Riemannian geometry. Why this is, you know, okay, I understand the point that this is, you know, model dependent, very dependent on the choice of differential calculi, very dependent sometimes on the choices that you make for the lifts of some maps, and exactly on certain conditions that you impose. But, you know, why it was so attractive that if in many, many cases, once you make those assumptions, you can compute the scalar of curvature. I mean, computing, for instance, the scalar of curvature in the spectral way for the non-commutative torus in the joint work with Ludwig Dąbrowski, we computed this so-called asymmetric non-commutative torus. So two-dimensional asymmetric non-commutative torus, when, so to say, each circle, actually one circle only is modified by a conformal factor. so the Dirac operator, or the metric on this one circle is modified by a conformal factor, which depends on, which is an element of the algebra of the entire non-commutative torus. And that was just, you know, almost impossible, and the result is not very, very tangible. On the other hand, when you do algebraic approach, this algebraic approach yields, so to say, much simpler and much more computable answer. This is not saying that this is, you know, good or bad. Neither is, so to say. The only thing is that, you know, it would be perfect, or maybe it would be good if one finds, you know, that at least there is some sort of consistency. I'm not saying that everything should be consistent. Maybe that there is at least some consistency in those formulas, or it is part of the formulas. So this is one of the things. Second things, so this is what I said, you know, that these things are manageable, and you can find, you know, constant curvature solutions. If you then want to put things on a computer, this is computable. The next thing is that, you know, it would be perfect, you know, to recover really some geometric things. So the original idea was that if you compute things on groups, I mean, cyclic groups are very simple, and one doesn't expect really, you know, anything illuminating, you know, from cyclic groups. But if you go to some more complicated groups, that for the constant metrics, the expectation would be that in computing these objects like the scalar curvature or integrated scalar curvature, or some tensors, one can get some objects, some things that would be related, intimately related to these groups. So this is something like linking, you know, the properties of these groups with this approach. It would be perfect. I mean, so far, you know, the only thing is that, you know, this geometry of this, the continuous limit, I mean, gives something that's related to the circle, and it might be a hint that, you know, maybe one should go this way. Now, the perfect thing would be also to have a good understanding what are the assumptions that one has to make. So the assumptions about the metric, how to understand the metric, how to understand those objects we want to compute, like the Ricci or the Riemann curvature, and relate them to the other computations. So for instance, I mean, in those fuzzy circles, fuzzy tori, fuzzy spheres, I mean, when one uses these Dirac operators or Laplace operators, this is all finite dimensional. So the spectra are finite dimensional, so one can't say anything about the asymptotics of the spectra. But going with the size to infinity and making some computations, one can see some behavior. So the question is whether those things that one gets using this algebraic approach could be related to something that could be that is computable using this spectral action or version of spectral action for fuzzy spaces approach. And finally, you know, even, I mean, the most interesting, one of the goals for the torus was to see what would be the limit for the torus, what would be the continuous limit for the torus. And this, you know, has to wait a little bit. I mean, because, well, I mean, we need to understand much better, I mean, what choices, so this uniqueness of choices and the understanding of the choices one has to make, how to do it. Okay, and what would be the meaning of this continuous limit, and what is the meaning of this continuous limit? As Alain said, I mean, something like a puzzle at the moment, and I think, I mean, it would be perfect, you know, to go and understand it better. So I think the link to spectral approach and using spectral approach is somehow also a challenge, and this is something which well, was the original motivation to start it, but it developed into just, you know, linear connections over a circle. So thank you very much for your attention. So I stop here.
Okay, thank you very much, Andrzej. We are clapping our hands. And we had already a bunch of questions and comments in between, but yeah, Gaetano, please go ahead.
Yes, I think Alain is first, but okay, can as you like. So one comment and some questions. One idea of John relating to the subject that although the freedom in the choice of the metric is lost or very much reduced, there is a larger freedom in the choice of the differential calculus, and this could be of interest for applications. So maybe you can comment on this. And then
okay,
regarding the sigma, I missed some point. Do you require it to fulfill the Braid equation or not?
I mean, the assumptions here were absolutely minimal. No, so what we required here was just to take a bimodal map.
Okay, because this is very natural if you want to extend the covariant derivative to higher tensor powers and so on. And also the metric, do you require to be symmetric under sigma or not?
No.
No. Because in a paper with John, we were requiring okay, the star structure on tensor products to be defined in a slightly different way from the one you showed, which is which I mean you can show again. You flip the order of the tensor factors, and if you do so, then the commutative limit, I mean, is not what you would expect, because in the commutative limit you should preserve the order of the tensor factors. So in order to get the correct commutative limit, you should also restore it by applying a sigma. I don't know whether this is clear. What I mean, yeah.
Yes. So actually, indeed, you know,
then if you also require the metric to be symmetric under sigma, then the two things, I mean, cancel each other in this particular case, and the definition of reality of the real metric turns out to be the same in this case. But I mean, if you don't require the metric to be symmetric under the sigma.
No, so metric is not symmetric under the sigma. The condition for the sort of compatibility of the linear connection with the star would involve sigma. Mm-hmm. If I remember it correctly. I mean, it's certainly in the paper. But you know, commenting on these restrictions on a metric. Yeah, I mean, you know, the point is that I always considered that, you know, the only case of a flat metric, for instance, for some non-commutative spaces, is not particularly, so to say, good in a sense that, you know, that if you this is very, very strong, and it's not really sort of justified. Even if you go to the spectral approach and you understand the metric as given by the Dirac operator, then you can have a lot of Dirac operators that don't give you this flat metric, this constant metric. So then one has to probably you know, somehow work around, or maybe maybe make less restrictive metrics. I mean, I have no idea, but I'm certainly, you know, thinking that it's, you know, the story of whether the approach to what is considered as non-commutative Riemannian geometry in all the approaches, I mean, in spectral, algebraic, or whatever approach, I think, you know, the story is not yet not finished. So it's probably to be continued. So any ideas are welcome.
But in a sense, also the choice of the Dirac operator is really related to the choice of the differential calculus in a sense. So
yes, indeed.
So I think.
But okay, yeah, you wanted me to comment on the choice of the differential calculi. Yes, the thing is, you know, that the differential calculi here is chosen to be, well, in a sense, I call it minimal. You know, that's you know, minimal in the sense, you know, that the sort of dimension is minimal. Yeah. But of course, I mean, if you have the interpretation of this then metric for this differential calculus, and if you have this interpretation of this function, I mean, in this discrete case, imagine that you take sort of even a universal differential calculus, and if you take the metric for this universal differential calculus, then it would be like you would have distances not between the nearest neighbors only. I mean, here you have like the distances between the left and right nearest neighbors and the oh, thank you very much, Piotr, for correcting. But you would have the distances, something like it would give you this differential calculus, and the metric for that will give you additional distances between different points. And this is something not really, when you want to really study something like the discretization of a segment or of a circle, that this is something like enough, or of a line. So this is the idea why this differential calculus needs to be minimal. But of course, you know, one of the things, this is just a not an idea, but I mean, nobody ever studied in the context of this non-commutative Riemannian geometry. Not even, I mean, in the spectral case or in the algebraic case, other differential calculi on usual spaces, on manifolds. Over the circle, you can have a differential calculus that, I mean, of course you can have universal, but I mean, universal might be a little bit too big, but you can have a differential calculus that involves second order derivatives.
ANDRZEJ, I mean, what you say is not right. I mean, on the circle, you have one calculus which is tremendously powerful and useful, which is the quantized calculus.
Oh yeah, there is a quantized calculus.
And
yes.
If you want to, for instance, what it allows you to do, which cannot be done at all in different ways, is that when you take the commutator with Hilbert transform, then you can integrate powers of the differential of an absolute value of the differential of a function to the power p, where p is the Hausdorff dimension, and then the Discretized gives you the Hausdorff measure. So I mean, this is incomparable with, I mean, it is in that you see the power of Hilbert space.
Oh yeah.
I mean, there is tremendous power in operators in Hilbert space, in the fact that the integral is replaced by the Discretized and such things. I mean, and this holds already for the circle. So if you want, one should remember that for the circle there is a quantized calculus, which you know, which is conformal, which has many facets to it. So I mean, one has to be careful when one says, you know, there is no something. I mean,
no. I was not saying that there's no something. What I was saying is that there are no computation of something like, say, this algebraic version of Riemannian geometry for other calculi.
Yeah, sure.
So this and for instance, these are the calculus, and there are some other calculi like the calculus that uses second order derivatives. I mean, so there's and two
No, I understand, but if
yeah.
you want, what I insist on is that if you want, in my mind, there is a universal calculus which
Yeah.
has tremendous power, which is the quantized calculus. And what I mean by that is that, you know, it's very hard to let people understand that. But if you read the Principia of Newton, you will find out that Newton had all troubles in defining what is a variable. And for him, eventually, he found that it was a function of time. But with the advent of the quantum mechanics, we have an infinitely better definition of what is a variable. And this is a real variable is a self-adjoint operator in inverse space. And then when you find out, you know, that you can differentiate, you can work with infinitesimals, you can take their absolute value, raise them to non-integral power. You can do things that you would never do even with distributions and so on. Then, you know, it's very tempting to say that somewhere in your mind, there should be a place for this quantized calculus. Now, okay, then if you want the trouble when one does things algebraically, it's very fine, you can compute and so on and so forth. But somehow you are missing the tremendous power of operators in Hilbert space. That's one thing on which I really want to insist on. I mean, it has nothing to do with the spectral triples and so on. It is something independent. I mean, you know, it is something which I think is the reflection of the discovery of people who discovered quantum mechanics. I mean, which is something tremendous, because I would even go further than that philosophically and say that if you want, it is a true notion of variability. I mean, Newton had reduced variability to the dependence on time, but the quantum teaches us that there is a variability which is in fact much more fundamental, and which is best embodied by this Hilbert space framework. I mean, so we have something extremely valuable there, and we need to use it more. You know, that's that's what I would like to say. I mean, but of course, okay, it's great to do these algebraic calculations, and I was quite indeed very interested by the formulas that you obtained for the classical limit. I mean, for the continuum limit. So this is very interesting for sure. So you know, I don't dislike at all this type of calculations, but of course, then at some point one should relate it to the quantum framework. I mean, to the Hilbert
Exactly,
framework.
exactly. This is perfectly like that. So, for instance, I mean, when one has this formula, I mean, there are formula for the non-commutative tori, for the conformal rescaling that are, for instance, by Rosenberg, right, which is purely algebraic. There's a formula. There's a formula which is spectral. There are formula that is obtained also in different way by Selve and Ludwig, which is also purely algebraic. You know, there should to be
of course,
way to communicate between those all
but
these
even
two sides.
I would say even, you know, you shouldn't be somehow put off by the fact that when you are in finite dimensions you don't have asymptotics, because the spectral action is really not asymptotic. I mean, the asymptotic formula is just an approximation to what it is. And so in finite dimension, what you are missing in order to do relevant calculations is not the action, because you can just take the trace of the suitable function of the Dirac operator. I mean, this still exists, of course, in the finite dimensional case. But what you are missing the constraint, like the Eier-Heisenberg relations, I mean, suitably made finite dimensional, that will prevent you to get the answer, which is zero. I mean, you know, so somehow, you know, what happens is that in the infinite dimensional case, because of the Heisenberg-Eier relations, you have kind of roof that prevents the solution to be zero. And then you can minimize, you can extremize, you can do all sorts of things. But surely the spectral action, I mean, the fact that you have to take an asymptotic expansion is only an approximation. I mean, the real world is surely quantum. And what we do, we filter out of this quantum world classical approximation, classical view, if you will. And this filtering is done by the Dirichlet trace, because the Dirichlet trace wipes out all the quantum details when you integrate. So I mean, this is something which will take time to digest, but okay, somehow, you know, the true stuff is really taking place in the quantum. I mean, there is very, very little doubt. What we have a lot of trouble doing is to guess, you know, as you were saying from the start, you were saying you want to approximate by finite stuff. Now, I should signal one paper which you should look at, which is a paper by Woodard. It's on the archive. He is a physicist. I think it's around 2008 or something like that, where he explained why it's not a good idea to approximate space by finite sets of points. And I mean, he has a physics explanation. So of course, this is open to a lot of discussions, but his physics explanation is pretty neat. I mean, the idea is that if you want, because of the expansion, there is a factor of around 10 to the 50 in the expansion of the universe. And then by looking at what happens at very, very small scale at the beginning, what he finds out is that, if you try to approximate by a set of points, then you run into a contradiction. And the contradiction is that your nearby points would be at a distance from here to the next galaxy in the actual times. I mean, you have to read the paper. You have to read the paper, but somehow, so I mean, this type of discussion is, I think, very, very important to have, because I mean, it's clear that we are trying to find the right angle towards, a form of quantum gravity. And I mean, the paper of Woodard is quite interesting because it discusses all possible angles at the time. And I mean, in a way which I think is quite intelligent. I mean, I think it's, I don't know if I have the paper here, which I could show you, but let me see.
And his name is Woodard.
Woodard, without an H. So,
okay.
Yeah, it's, let me try to find, no, I don't have, I don't seem to have a good, unfortunately, I mean, which is unfortunate because I would really like to show it to you, but I will send you to, I will send it to you.
Okay.
I will send it to you by mail. Yeah, I will send it to you by mail. I think it's worth looking at, because, we often have this kind of introduction when we say about quantum gravity and so on. No, I mean, one has to be very careful. One has to be very, very specific and careful, I think. Yeah.
Okay, this was very interesting. I love such discussions. This is one of the reasons we are running this seminar. Anybody else? Any comments or questions?
Yes, I have a maybe comment and a question.
Okay.
If you assume that this G, this metric, is sigma symmetric, you can easily mimic the definition of a Clifford algebra, of the Clifford algebra of this metric. Okay.
Mm-hmm.
My question is, did you try to define spinors in this?
Oh, no. I haven't. No, there was. Yeah, I mean, the point is that to define spinors. So spinors just by mimicking the Clifford algebra from the metric and through the metric and the sort of sigma compatibility. No, we haven't done that. We haven't thought about spinors. Then, of course, I mean, having spinors and having something like that, one can try to leave the Levi-Civita connection, but no, we haven't tried.
Okay, so my second question is gone. It was about this braiding condition, but I have some minor, more specific question. What about the condition, the relation between the sigma and multiplication on the level of omega-1? Is you do not assume that it is antisymmetric with respect to
No. So you see, I mean, the only conditions in sigma that appear are the conditions that appear from the torsion-free condition.
Mm-hmm.
This is the only thing that where the wedge, somehow intervenes. Wedge composed with sigma is something. I mean, nothing like the anti-symmetry or is predefined. This comes as a result. So, for instance, the sigma has to be a bimodule map, satisfy this condition so that the connection is torsion free. That's all. Nothing else.
Mhm.
So sort of, you know, like looking, I mean, these are, you know, like the minimal conditions. I mean, the minimal conditions that you assume in the geometry. I mean, you have, of course, you have the metric which is symmetric. So this is one thing. But then, you know, the sort of symmetry of the metric is a different thing. I mean, sigma here is part of the linear connection.
I understand, but classically, the uniqueness of this Levi-Civita connection is a consequence of some play between symmetrization and anti-symmetrization.
Yeah.
If you don't mimic this classical effect, how can you expect this non-commutative analog of uniqueness of the Levi-Civita?
This is, you know, this is a very good question. So, for instance, I mean, if you look at the works where this uniqueness was shown, these are the papers by Jagielloński, Goswami, Devashish Goswami, and co-workers. So there was actually, you know, for the differential calculi, when you have some sort of generalization, I mean, I would say it like that, generalization of this property, and then you go like that, and then basically what you do, I wouldn't say you mimic, but you use the arguments that are very similar to the classical arguments to get the uniqueness. I mean, but this works only for some specific differential calculi. I mean, and not doesn't work always, and doesn't work in the general case. I mean, we didn't assume that here. We didn't assume anything more than, you know, what is sort of needed. Why? Mostly because, I mean, the idea was to see what is this sort of maximal space when you can get some reasonable results. Sometimes when you assume too much, I mean, you get nothing.
Mhm. Okay, what can I ask the last question?
Sure, go ahead.
Did you try to compute cohomology of this differential graded algebra? Is it trivial or?
Yeah, that is, I think that is trivial, yeah.
Mm-hmm.
I mean, in this case, this is true. I mean, I don't remember that because, I mean, but this has been computed many years ago. I mean, people wrote something about it many years ago. Yeah.
Okay.
Okay, thank you, Tomek. Anybody else?
Maybe it is a silly question, but I would like to ask how this notion of existence of connections deals with the situation where you have a topological space, and this space cannot be given a structure of a manifold.
And the space cannot be given a structure of a manifold. Ooh.
This is somehow reflected in this non-existence of connections and or metrics for topological space which are not manifolds.
Which are not manifolds. I have no idea. I'm sorry.
Okay.
Okay, anybody else? If not, let us thank ANDRZEJ again. I have to find this. Yes, clapping hand. Okay, so thank you very much, ANDRZEJ. Thank you all for attending.
Thank you very much. Thank you for discussions. And I see there was also a discussion on chat.
Yes, behind your back. Yes.
Yes, behind my back about muon physics. So some physics, muon physics broken at 4.2 sigma.
Yes.
So,
yep.
Which is a good sign, you know, something is broken then.
The definite number is 5 sigma, actually. Just for complete to make the information complete.
Mm-hmm.
Once it's 5 sigma, it's accepted.
Mm-hmm.
Yeah, but you know, I mean, probably I wouldn't be hurrying, you know, with champagne because there's been many events that's been broken at, I don't remember, you know, what sigma, and then later it was corrected. But so
Yeah, that's different story.
That's different story.
But, yeah, that's a different story. Yes.
That's a different story. That's a different story.
But may I ask where has the news come from CERN or where from which lab?
From John Barrett.
Fermi Lab.
Yeah. Thank
Oh,
you,
it's
John.
Fermi Lab.
Ah, from Fermi Lab. Okay.
The latest is Fermi Lab.
Okay, I see. Thank you very much.
Yeah, Fermi Lab Twitter, yes.
Mhm.
Okay, so before we adjourn, let me just mention that in a week, our speaker is Konrad Aguilar, so it will be non-commutative metric geometry in the spirit of Riffel and Lafreniere. Okay.
And Piotr, maybe can I make one announcement that might be, interesting for some people? I mean, I try to reach some people.
Go ahead.
There's a
paid commercial. You owe me a beer, okay?
Yes, I owe you a beer after we all can meet. Anyway, there could be an interesting seminar on Friday at 2 p.m. Local Warsaw time. This is joint Warsaw-Krakow Poznań seminar with a speaker from Serge Pontoise about Lorentzian spectral action. So something like relevant. If you want, just go to, I mean, what would be? I can write in the chat the address. I mean, so,
Write in the chat the address, just to be
yes.
safe side.
So the address of the talk. Just I need to of the web page where the talks are announced. So this is the web page. Sorry, everyone.
Go there.
Yes, so I sent so then this is by Michał Wrochna from Serge Pontoise about spectral action on, so it might be interest to some of you, so.
Okay.
We'll be happy if you're there. So thank you very much.
Thank you.
And with this announcement, we adjourn, and I hope to see you guys next week at the talk of Konrad Aguilar. All the best till next week. Bye-bye.
Next week. Bye.
Bye-bye.
Bye. Bye.
Ciao.